So this is the next video, and in this video what we will see is that we will see about the dot product, and we will see about the cross product. So this video I will mathematically define both the dot product and the cross product, and after mathematically defining I will solve an example using both the dot product and cross products to demonstrate the working. So to apply the dot product, or to mathematically define the dot product, what I will use it, I will consider two vector in space. So this is a vector A and this is another vector B, or to represent them from the specific Cartesian coordinate system. So considering this is a Cartesian coordinate system with x, y and z, and this is a vector A and this is another vector B, and the angle between A and B is theta. So it is said that if you are having two vectors A and another vector B, you can find a dot product between A dot B. When you are finding a dot product, whatever result you are getting will be a scalar quantity, and this result can be, so this is a scalar quantity, it will have only magnitude. And when you are finding A dot B, it can be written as the magnitude of A into magnitude of B. So continuing, if you are having two vectors A, B, and if you are taking the dot product, you can write it as A multiplied by B and replaced by the cos of theta, or the angle between A and B. So, and whatever result you will get in this case will be always a scalar quantity. So we will just, so it's taking that whole idea further. You are having a vector A which you are representing in the Cartesian coordinate system like Ax divided by unit vector of x plus Bx divided by unit vector of y, By divided by unit vector of y, plus Cz divided by unit vector in the direction of z. So this is a vector A which I am having, and this is a vector B which I am having, could be represented as Ax, just taking so taking to represent the vector A, it could be represented like Ax, the direction of x, plus By plus Ay in the direction of y, plus By, which is, or Az, which is a magnitude in the direction of z. And again you have a B vector, you can write it as Bx with Ax, the magnitude direction of x, unit vector in direction of x, plus A plus by with a direct magnitude in the direct unit vector in the direction of y, plus bz with a magnitude in the direction of z. So simply saying, what you have is, you have a coordinate system and you have one vector a here and the other vector b here. So this can be represented in this way. This vector can be represented in this way. So this is x, y, z. So when I'm taking a dot b of this vector, what I'm getting is, I'm multiplying this both, that is a into b, that is ab into cos of theta, or the angle between the two vectors. So it will be ax into bx and into ax dot ax plus ay into by into ay dot ay plus az into bz into az dot az. When I am having two vectors like the unit vector ax and again the unit vector ax, so the angle between these two vectors is 0. So when I am applying the dot product here, that is a into a, the magnitude of a into magnitude of a into cos 0. So the magnitude is 1, the magnitude is 1, cos 0 is 1. So all this will be 1 here, 1 here, 1 here. So finally what I will have is a dot b will be ax into bx plus ay into by plus az into bz. So this is how I am getting only magnitude when I am doing a dot product of two vectors. So that's how I just demonstrated. You will get only the scalar part, and this is how you can really apply that. Again, why in this same example, why I did not consider the multiplication of ax dot ay when there will be vector ax dot, that is the direction of the x and the direction of the y. The angle will be 90 degree. So what will happen? It will have the magnitude of a, magnitude of ax, magnitude of ay into cos of 90 degrees. So this will be always equal to 0. So I have taken only the consideration of the x here. So, and the next case is going into more detail. What you will get is something known as the vector product. So vector products are not easy, they are hard to understand. And again, you are having a Cartesian coordinate system to represent the vector. So you are having x, y, z, which is a Cartesian coordinate representation. Suppose you are having a vector and you are having a b vector, and the angle is theta, then a cross b will be always a vector, and it will be given by a unit vector in the direction perpendicular to both a and b. And given by AB sine of theta of angle between A and B. So again, if to find out the direction in which this vector will be there, whether it can only be perpendicular, it can go in this direction or it can go in this direction. On if suppose if a vector is located in a plane, I have a vector which is origin, and if I have vector A here and I have another vector B here, and these are my two vectors, and now I am having a cross product of A cross B, and when I am moving from A to B, I will be moving in this direction clockwise. So while I am moving from A to B, I will be moving upwards. So my AN will be always in the upwards direction in which my screw will move when I am moving in the clockwise direction. Again, if I am having a B cross A, this will be always equal to minus of A cross B. So to represent that, simply you can say that now you are moving in the opposite direction, so my screw will be going downwards. So this is my AN in that case. So that's how you're representing your AN. So to simply understand that by taking example, so if you have a vector A which you are representing as if you are having a vector A which you are representing as AX of AX plus AY of AY plus AZ of AZ, and if you have another vector which you are representing as BX of AX plus BY of AY plus BZ of AZ. So these are my two vectors. Now I am applying the cross product. I am going to apply the cross product. So what will happen when I apply the cross product? So that's A cross B which I am going to apply here. So that can be defined as A raised to N, which is the direction, and AB magnitude into sine of theta AB. So when I have two vectors and I'm applying this to each and every so in these two vectors, these are my vectors, these are only my magnitudes. So when I will applying the cross product, I can write it like A cross B in detail as AX into BX, which is a magnitude, and AX vector cross AX vector plus AX into BY into AX cross AY plus AX into BZ into AX cross AZ, and plus AY into AY plus AY into BX into AX into AY, and plus AY into BY into AY into AY plus AY into BZ into AY into AZ, and again plus AZ into BX into AZ into AX plus AZ into BY into AZ into AY plus AZ into BZ into AZ into AZ. So this is my total which I get. So what is my understanding of this is that the AX into AX component, AX cross AX, the angle between them is 0, So my sine of 0 is always 0. So this will cancel out. Again, this is cross, sorry, this is cross, this is cross, this is cross, this is cross, this is a cross product. So all the vectors like which is multiplied by itself will be 0. And again, when I'm having two vectors, like if this is my x, y and z, so this is my ax and this is my ay, so I'm moving from x to y, so my ax cross ay will be a vector. If I'm moving in this direction, it will be always a vector which is going in the z direction, so it will be az. So whenever I'm having case where, like in this case where ax cross ay will be always my az vector. So if I'm substituting all this, it's possible to get an answer, which I will just write down. And again, the case is like you're having a y cross ax, so you're moving from y to, so you're moving in this direction, so your screw is going down, so it's minus az. So you'll have both positive and negative values, and when you are solving this full equation, what you will get, you can represent it something like a cross b, which is a vector which will be given by ax, ay, az, and which can be given in a matrix form. This is a matrix, so you'll have to solve the matrix and find the solution. So it can be written in by ax, ay, az, bx, by, and bz. So simply this is from the previous solution which we have done. This is from the previous solution which we done in the previous step. So from that you will get something like this. And to write it in detail, it will come like this. So to solve this, if you are solving for this, you'll have to multiply this way, and again you will have to solve for the full solution, so that's coming as part of the matrix. So this is how you are representing it using the determinants and everything, and this is how you represent it. So what we saw in this lecture was we saw how we are mathematically defining the cross product of two vector, dot product of two vectors. So if there are two vector which is dot product, we can represent it mathematically as a b, the magnitude of a and b, and cos of angle between a and b, and this will be always a scalar quantity. And if you have a cross product of two vectors, and you can represent it by the magnitude of a, the magnitude of b, and the sine of angle theta between a and b, and there will be a direction which will be the direction perpendicular to direction of a, and when you are moving from a to b. So if this is a vector a, this is a vector b, the direction will be always so of the plane in which you are lying. So simply saying that if you have vector representation is possible. So if your vector which is a is this vector and b is this vector, so to find out the direction of this neutral or direction in which the resultant vector will go, you will have to project it in a plane. So when you are projecting it in a plane, you will bring it down. You just project this in a plane, so it will become like this. You can project it from this 3 space. This is a y coordinate, this is a x coordinate, and this is a z coordinate. Representing that, you are simply representing it using what is this, and this is my b vector and this is my a vector, and this is an angle theta ab. So you have from the space representation, well, from the 3 space representation, you are representing it in plane, and now you will move from b to a to b. So you are moving from a to b. So when you are moving from a to b, your right hand, the screw will move up, so the direction will be always in az. The direction in this case is in az. So that's how so this direction will be always, it will be towards the upper plane or towards the downer plane in the positive z direction, or the plus z direction, or the negative z direction, minus z direction. So that's how you are applying the dot product and the cross product, and we saw that. Now next, in the next lecture, I will simply take one example of the dot product and the cross product, and I will solve it to the full. That's all.